Okay, good morning to everybody. In this lesson, I will start addressing a new topic, the last one in this course this year, which is related to spheres, spherical waves, and scatterings from spheres or radiation in the presence of spheres. The motivation for this is that I would like to introduce the so-called Watson transformation, which is a technique in electromagnetics that exploits complex integration. In particular, it is a sort of reverse residue theorem because it converts a series into an integral, and it's able, as we will see, to convert a slowly convergent series into a rapidly converging one. And actually, today, in the second part of the present lesson, I will illustrate you this technique by following the paper that was written by George Neville Watson originally in 1918. However, in order to do so, we will need to introduce a number of concepts about spherical waves which are usually not treated in basic electromagnetic courses, at least in our curricula. So in the first part of this lesson, I will give you some basic information about spherical waves. So let us start with considering the simplest spherical waves, those which are scalar, and therefore we have scalar spherical wave functions. We will indicate with the letter psi any general scalar wave function, which means, by definition, a solution of the scalar-Helmholtz equation. Let me enlarge the screen. Okay. Now, if we write this in spherical coordinates, the Laplacian will become, as you can see here in the box, the sum of three contributions containing derivatives with respect to the three spherical coordinates r, theta, and phi. And we will try to find solutions to this partial differential equation by the method of separation of variables. Let me admit someone else, or no, maybe there is no one. Okay, sorry. By separation of variables, we mean to seek solutions in the form of a product of three distinct functions, each of which depends on a single spherical coordinate. So we have capital R, which depends on R, capital theta, which depends on the angle theta, and capital phi, which depends on the angle phi. And we will call spherical wave functions obtained by the separation of variables, and we will proceed in the usual way. So we plug this specific form for psi into the scalar-Helmholtz equation. And if we further divide by the wave function itself, psi, and we multiply by the term r squared times the squared sine of theta, what we obtain is this form for the Helmholtz equation, in which we have achieved the goal of isolating a term, which is the third addend, the one that contains the double derivative with respect to phi, which depends only on the spherical coordinate phi. So we know, with the standard argument, that now this term must be a constant, and we choose as a name for this constant the quantity minus mu squared. So our term 1 divided by capital phi times the double derivative of phi, with capital phi with respect to the coordinate phi, is equal to this constant, minus mu squared. Okay, once we have done this, we can replace the third addend in the equation by the constant minus mu squared. And if we further divide the entire equation by the square of the sine of theta, we obtain this alternative form, in which now you see there is the constant mu squared inside the equation, and in which also we have managed to separate the dependencies on the remaining coordinates r and theta. Let me see if there is. Okay, here we have Buongiorno Carlo. I don't know if he managed to enter this. Ok, buongiorno Carlo, mi sente?
Sì, buongiorno a tutti.
Buongiorno, stavo... Okay, so now you can see that the first addend and the last one depend on r, whereas the remaining addends depend on theta, so they must both be constants. In particular, the dependence on theta can be equated to a constant, and we will write this constant in this particular fashion, minus ni times ni plus 1. And the reason for choosing this particular form for the constant is that, as we will see, when ni is an integer parameter, then the theta function has some special properties. So it's useful to write the constant in this way. By doing so, and replacing this, substituting back into the equation above, we finally have the dependence on r alone, okay, in which the constant ni times ni plus 1 also occurs in this equation. So finally, by separating variables, starting from the scalar Helmholtz equation, we have managed to obtain 3 separate ordinary differential equations. The first one contains the dependence on r, the second one, the dependence on theta, and the third one, the dependence on phi. This is the usual approach that I'm sure you have seen many times in using the techniques of separation of variables for deriving, for example, plane waves as a solution of the Helmholtz equation, or in many other cases. May I ask you to close your microphone, please? So now we will examine separately these 3 ordinary differential equations, starting from the first one, that is the radial dependence, which is contained into the r function. Now this function r is closely related to the Bessel functions. In particular, it can be written as a combination of the so-called spherical Bessel functions. We will use the letter, the lowercase letter b, to indicate a general spherical Bessel function of order n, which, as you can see from this equation, is related to an ordinary Bessel function indicated with the capital letter b, with order n plus 1/2. The argument is k times r, and in front of the ordinary Bessel function, we also have this factor, which depends inversely on the square root of the argument k times r. This holds for any cylindrical function, so these b functions could be the function j or y, so the Bessel functions of the first and second kind, or also the Hankel function of the first and second kinds. Now, in spite of this definition, which seems a bit complicated, actually the spherical Bessel functions are quite simple functions, much simpler than the ordinary Bessel functions. In fact, if you examine the first orders, the spherical Bessel function j of 0 order is nothing but the ratio between a sine function and its argument, kr, whereas the Bessel function y, spherical Bessel function y of 0 order, is the ratio with a minus sign between the cosine of kr and kr itself. So, as you can see, J0 is a regular function for any value of the argument because it has a removable singularity at the origin, whereas the y function is singular at the origin with an algebraic singularity of order 1. The Hankel functions are ratios of traveling wave exponentials of e plus jkr or e to minus jkr times, divided by jkr or minus jkr. So the form is quite simple, and if you go to higher orders, you will discover that spherical Bessel functions are polynomials in the reciprocal of kr multiplied by trigonometric functions, so either sine or cosine with argument kr. Let us now go to the theta dependence. The equation in theta is related to the so-called Legendre equation, and so its solutions are called associated Legendre functions. We will indicate those generically with the letter L, with two indices. The lower one is ni and the upper one is mu. The argument is the cosine of theta. And this is, in general, a linear combination with complex coefficients of two special kinds of associated Legendre functions, those indicated with the capital letter P and those indicated with the capital letter Q. The first ones are the associated Legendre functions of the first kind, and those are regular for any theta in the interval between 0 and pi, which is the physical range of variation of this spherical coordinate, only when the lower index, ni, which is related to the radial dependence, is an integer function, okay? Whereas the second kind, associated Legendre functions, Q, those are singular when theta is equal to 0 or pi for any value of the indices ni and mu. Here is an illustration of the Legendre functions, in the particular and the lower index, ni, is equal to an integer, n. In this particular case, though the associated Legendre functions are polynomials, they are simply polynomials in the cosine of theta. They are called Legendre polynomials, and they satisfy this simplified version of the Legendre differential equation. Here in the plot on the right, you can see the representation of the first few Legendre polynomials. The one of order 0 is a constant equal to 1, so it's a flat horizontal line. Then we have the polynomial of the first order, which is linear in the cosine of theta. Here you can see on the horizontal axis the angle theta. So you will see the cosine of theta that goes from 1 to -1 in the indicated range from 0 to pi for the argument. And so on. All the others are oscillating functions more and more as the index increases. All of those functions pass through the value 1 when the argument is equal to 0, whereas they are equal to 1 or -1 depending on the order when you are at the other extreme, that is when theta is equal to pi. When the lower index, the upper index mu is an integer, but it is strictly larger than 0, and still the lower index is an integer, n, then the functions can be expressed in terms of derivatives of the Legendre polynomials multiplied by this factor 1 minus u squared to the power m divided by 2, with the result that when m is an even integer, here we have the derivative of a polynomial multiplied by an integer power of the binomial, and so therefore the associated Legendre function remains a polynomial, whereas when m is an odd integer, this is not true anymore, since we have the square root of 1 minus u squared coming from this term here. But in any case, in this particular, with this particular choice of the indices, the Legendre functions are still represented by elementary functions. We may also mention an important property of Legendre polynomials, and more generally of Legendre functions, that is their orthogonality and completeness in the interval from 0 to pi. For example, the orthogonality statement is the one that you can find here, an integral from 0 to pi of the product of two Legendre polynomials with different orders, with general orders n and q, when integrated with respect to the cosine of theta, that is with respect to the argument of the polynomials, is equal to 0 if the orders are different, so if n and q are different, and it's equal to a constant, as you can see here, 2 divided by 2n plus 1, when n is equal to q. This symbol here, this delta with two indices, is the Kronecker symbol, which is equal to 1 when the two indices are the same, and it's equal to 0 when they are different. So it's a sort of discrete version of the delta function. So this is orthogonality, whereas completeness means that you can expand an arbitrary function f of theta as a series of these Legendre polynomials, so obtaining the so-called Fourier-Legendre series, in which we have these coefficients, in general complex coefficients, a sub n, which can be evaluated by exploiting the orthogonality property, that is, projecting both the left and right hand sides onto the basis, the orthogonal basis constituted by the polynomials themselves, and thereby obtaining an expression for the coefficients, which is an integral from 0 to pi of the product of the function that you wish to expand times the nth polynomial, p sub n. Okay. Finally, we have the angular phi dependence, and that's the simplest one, since we have the familiar harmonic equation for the dependence, and therefore we have, in general, linear combinations of either trigonometric functions with argument mu sub times phi, if you prefer a standing wave representation of the dependence, or if you prefer a traveling wave representation, then you may use complex exponentials e2 minus j mu phi or e2 plus j mu phi. Buongiorno, Riccardo. So if you wish to have a single-valued wave function in the physical range from 0 to 2 pi that is covered by this spherical coordinate, then of course, as you know, this constant mu must be an integer, so we can write it as m. On the other hand, if the spherical coordinate phi does not cover the entire range, but it covers only a restricted range, this depends on the particular boundary conditions of the problem, then in this case, mu may also assume non-integer values, okay? The general representation for a scalar wave function in spherical coordinates, having proceeded with the separation of variables, is therefore the linear combination of elementary solutions obtained by multiplying together the three kinds of functions that we have described so far. So the radial dependence is described by the B functions, which are spherical Bessel functions. The theta dependence is described by the associated Legendre functions of the two kinds. And finally, the phi dependence is described by the usual trigonometric or exponential functions. Here we have undetermined coefficients C, which can be derived considering the boundary conditions of the problem at hand. So they depend on the specific problem you are trying to solve. Just to illustrate some kind of configurations in which you would use spherical coordinates, for example, if you study conical regions, or better, regions bounded by cones, then in this case, the angular range for the spherical coordinate theta is limited between 0 and some upper value, theta 1, so it's not the entire range. So in this case, whereas the azimuthal coefficient mu is an integer, the other angular coefficient, that is the lower coefficient of the associated Legendre function, is not an integer in general, so we rewrite it with the Greek letter ni. And the same occurs in other situations in which you still have conical boundaries. For example, here at the bottom you would see the junction of two cones with a common apex, and this could be a biconical antenna, for example, or the two cones with a common apex could share the same axis. So you would have the region between the two cones with different half apertures. In this particular case, in these two latter particular cases, we may note that the z-axis is excluded from the region in which the electromagnetic field exists. And since the associated Legendre functions of the second kind are singular along the z-axis, in these latter two examples, you may employ those Q functions, whereas you cannot employ them in the first two examples, because there the field should be regular also on the z-axis, and the Q functions are singular on the z-axis. Other examples could be the angular wedge-shaped regions in which ni is now an integer because the angle theta goes from 0 to pi, whereas phi covers a restricted angular range, so its index, mu, is in general non-integer. Of course, you can also have this situation, the last one, in which you have restricted ranges for both theta and phi. And so in this case, which could be, for example, a conical horn, a spherical horn antenna, you would have non-integer indices, both as concerns theta and as concerns phi. So all these are examples of structures that you could study. You could see them as radial waveguides, so waveguides in which the waves propagate radially and that are defined by boundaries with respect to theta and phi. Okay, so far we have discussed the simple scalar spherical wave functions. Now let us introduce the more complex vector spherical wave functions, which are needed because we wish to deal with electromagnetic fields, which are vector fields. Okay, in order to represent any electromagnetic vector field in terms of a scalar spherical wave function, one possibility is to use those scalar wave functions as one of the rectangular components of the vector potential, because you know the electromagnetic field can be expressed in terms of vector potentials, E, the magnetic potential, or F, the electric potential. For example, you could use a Cartesian coordinate. For example, you could employ a magnetic potential A, which has only the z coordinate, and that z coordinate, as you know, is a solution of the scalar Helmholtz equation. So by definition, it is a scalar wave function, which you can represent as a scalar spherical wave function, that is, with its dependence on r, theta, and phi. Now, this would be a rather hybrid representation because we are employing a Cartesian unit vector together with a spherical wave function. So to be consistent, we should write the Cartesian unit vector of the z-axis in terms of the unit vectors in the spherical system. So if you do so, you will find that z0 can be written as r0 times the cosine of theta minus theta 0 times the sine of theta. And this is one example of a magnetic potential in spherical coordinates that would generate a field that is transverse magnetic with respect to the z-axis, as you know from elementary electromagnetic courses. If your magnetic potential has a single component along a single axis in space, then the relevant electromagnetic field will have a magnetic field with no component along that axis. So therefore, a field which is transverse magnetic with respect to the axis. Now, the reason why we can proceed in this way is the one I have already mentioned. If we assume that this potential is a Lorentz potential, that is, potential that satisfies the Lorentz gauge, in a source-free region, this vector potential would satisfy the vector Helmholtz equation, and in Cartesian coordinates, the Cartesian coordinates of the Laplacian are equal to the Laplacians of the Cartesian coordinates. For example, the z-coordinate of the vector Laplacian of A is equal to the Laplacian, the scalar Laplacian, of the scalar coordinate A sub z. So therefore, any Cartesian coordinate satisfies a scalar Helmholtz equation, that is, it is a wave function. You can do, of course, the same with the other kind of potential, so the electric potential, F, and one could show that in any source-free region, any arbitrary electromagnetic field can be constructed by a superposition of a TM and TE field. So therefore, by proceeding in this way, you would represent an arbitrary field. There is an alternative to using Cartesian potentials, which is somewhat simpler in the algebraic developments with respect to the Cartesian ones, and it is the possibility to use radially directed vector potentials, that is, potentials either A or F, which have a single non-zero component in spherical coordinates, that is, the radial one. However, the problem with using radial potentials is that if you assume that your vector potentials A and F are Lorentz potentials, therefore they satisfy a vector Helmholtz equation, then in spherical coordinates, the radial components A sub r or F sub r would not satisfy a scalar Helmholtz equation, because in spherical coordinates, it is not true that the radial component of the vector Laplacian of the potential is equal to the Laplacian of the radial component of the potential. So we would not have spherical scalar waves as components A sub r and F sub r. In order to make use of what we have found for the scalar wave functions, we should use a different gauge. That is, we do not use the Lorentz gauge, but we do something different. So we start from the representation of the electromagnetic field in terms of mixed potentials, that is, in terms of both a vector potential A and a scalar potential V. If you employ the second Maxwell equation, you would find that in a source-free region, the double curl of A minus k squared of A is equal to minus j omega epsilon sub c times the gradient of the scalar potential V. Now, let us examine this equation, which is a second-order equation in the two potentials, A and V, in particular, by assuming that the vector potential is radially directed. So it has the single non-zero component A sub r. If you project the equation onto the theta and phi directions, so in order to get the theta and phi components of the previous equation, what you get is what you can find here at the bottom. The double derivatives of the component A sub r with respect to r and theta, or with respect to r and phi, are proportional to the derivatives of the scalar potential V, respectively made with respect to theta and with respect to phi. So by inspection, you would find that these latter two equations would be satisfied if you choose the scalar potential V such that it is related to the vector potential A by the equation that you can see here on top. That is, the scalar potential V should be proportional to the radial derivative of the radial component A sub r of the vector potential. And this is a relation between the vector and scalar potential that fixes a gauge. However, this gauge is not the Lorentz gauge, because the Lorentz gauge tells us that the scalar potential is proportional to the divergence of the vector potential. And now, if you evaluate the divergence of the vector potential, assuming that it is radially directed, you would discover that the expression for the divergence is different from what you can see at the left-hand side in the above equation. So we are working in a different gauge, and if you assume this different gauge, then the remaining component of the equation, that is the r component, can be written as you can find at the bottom of this slide, which is a quite complicated looking equation. However, if you manipulate this equation a little bit, you can discover that this equation can be written in terms of a simple Helmholtz equation, that is the sum of a Laplacian plus the constant k squared, applied not to A sub r, but to the ratio between A sub r and the radial coordinate r. So, of course, the dual equation would hold for the electric potential F. We may conclude that A sub r and F sub r are not spherical wave functions. However, their ratio with respect to r is a spherical wave function, and those ratios we will indicate with the symbols psi therefore, for example, the magnetic potential A can be written as the unit vector in the radial direction, R0 times R times psi A, or synthetically as the position vector R times this wave function psi A, and dually for the electric potential F. Now, those scalar wave functions, psi A and psi F, are known in the literature as the electric and magnetic Debye potentials, respectively. And as you have seen, they can be used to construct radially directed vector potentials A and F in a gauge that is not the Lorentz gauge. What's their use? Well, once you have the potentials, you can calculate the fields, and in a source-free region, the fields can be evaluated immediately as curls and double curls of these Debye potentials, vector Debye potentials. And furthermore, these relations in the box, so this representation for the field, can be shown to be sufficiently general to represent an arbitrary time harmonic electromagnetic field in a source-free region of space contained between two spherical surfaces with radii r sub 1 and r sub 2. So it is a very general representation for the field. Here it should be electromagnetic field, of course, not electromagnetic region. That's a typo. Now, since the bi-scalar potentials psi A and psi F are always multiplied by R in the construction of these vector potentials, as you can see, there is always the factor R in front of psi A and psi F. It is convenient to employ alternative spherical Bessel functions defined by Shelkunov originally, by multiplying the spherical Bessel functions, small b, with argument kr, times their argument kr, thereby obtaining the Shelkunov Bessel functions that are indicated with a capital letter and with a hat. And those are related to the ordinary Bessel functions b with order n plus 1/2 and argument kr, through this factor, which is proportional to the square root of the argument kr. Note that these Shelkunov alternative spherical Bessel functions will satisfy a different ordinary differential equation, which is reported here with respect to the ordinary spherical Bessel functions. And once we have introduced these modified Bessel functions, we can represent our radial potentials in terms of linear combinations of elementary solutions written as products of the elementary way of the special functions b hat and L and H. So this is the most general representation for the Debye potentials that we can use to represent an arbitrary electromagnetic field. This is the explicit representation of the field in terms of the radial potentials A and F, in which I have used two different colors for the terms that come from the magnetic potential A. Those are in blue, and those are the transverse magnetic part of the field, where now transverse magnetic is with respect to the radial direction. Whereas in red, I have indicated the terms related to the radial electric potential F, which produces a TE field, so a transverse electric field, again, with respect to the radial direction, R. Okay. Okay, so now we are in the position of, once we have introduced the spherical waves, both the scalar and the vector spherical waves, we are in the position of considering what are possible sources of spherical waves, and those are very familiar because the sources of the lowest order spherical waves are simple elementary currents, so current elements like dipoles. For example, if you have a single electric current element, there is an elementary dipole, also called the Hertz dipole, carrying an electric current I with a length L, and it's placed at the origin of our reference system, parallel to the z-axis. Then you know that this would radiate field that is Tm to Z, and which can be derived from a z-directed magnetic vector potential. And we know from basic electromagnetic and antenna courses that the expression for AZ is just the free space Green's function, e2 minus j kr divided by 4 pi r times I times L. Or, now we know that this is proportional to the spherical Bessel function H, Hankel function H of order 0 of the second kind, so we can also write this AZ component of the vector potential as proportional to the spherical Bessel function H of order 0 and of the second kind, through the coefficient that you can see here. Once you have the potential, then you can calculate in the customary way the fields by taking the curl of the potential to obtain the magnetic field, and then by calculating the electric field by using this combination of A and the gradient of its divergence. That's the standard formulas taken from basic electromagnetics. If you wish spherical waves of a higher order, for example, of order 1, you can still employ current elements, but you should use pairs of current elements closely spaced to the one to the other in the vicinity of the origin. For example, if you employ two opposite directed current elements separated by distance s close to the origin along the z-axis and parallel to the z-axis, then the vector potential that would be produced by those two sources in the limit when their spacing goes to 0 can be shown to be proportional to a spherical wave function of order 1, in which you have a spherical dependence in terms of h1 and Legendre polynomial p with order 1 and argument cosine of theta. So in this case, the indices would be n equal 1 and m equal 0. I remind you that m is the index related to the azimuthal dependence. So in this configuration, we have rotational symmetry around the z-axis. So the order m is equal to 0. If you place the two current elements along the x-axis, maintaining them parallel to the z-axis, a different result would be obtained, because now the rotational symmetry around the z-axis would be destroyed. And in particular, now what happens is that we have a Legendre function p11, and in addition, we have a dependence on phi through the cosine of phi. So in this case, the index m is equal to 1. Note that the field produced by an elementary dipole placed on the z-axis, the only non-zero components are h phi, er, and e theta. So this field is not only transverse magnetic with respect to the z-axis, but it is also transverse magnetic with respect to the radial axis. And therefore, we may find its field also through a radially directed magnetic vector potential. If you place your dipole at the origin, then you should employ a radial wave function of order 1. As you can see here, we have the function h hat of order 1 times the Legendre polynomial p of order 1. This would define a wave function indicated here with the blue color, psi a, that multiplies the radial coordinate r. So this is a Debye potential, a scalar Debye potential, expressed in terms of wave functions of order 1. Once you have this Debye potential, you would find the electromagnetic field through the relations reported below. So in this case, again, n is equal to 1 and m is equal to 0 by rotational symmetry around the z-axis. If you displace the dipole off the origin, so you place it at some place r prime with a distance r prime from the origin, and it is also possible to employ a radial wave function. And this time, this would be the bipotential. The previous one, sorry, is no, the previous one, okay, is performed in terms of a first order Bessel function, whereas in this case, the bipotential that we may employ is of 0 order. As you can see here in the blue term, we have a wave function psi a that is proportional to the Hankel function of order 0. However, note that now, in addition to the Hankel function, we also have r prime in the denominator, so the distance between the dipole and the origin. So the bipotential would go to infinity when r prime goes to 0. So if you let the dipole approach the origin, this potential would go to infinity. However, you, as an exercise, you could check that in this limit, you are still able to recover a finite field, and that's the correct field that would be produced by a dipole placed at the origin. So it is possible to use a radially directed zero-order Debye potential if the dipole is outside the origin. And before doing our break, I will introduce some useful wave transformations in spherical coordinates. The first one is the representation of the familiar plane wave in terms of spherical waves. Consider, for example, a very simple scalar plane wave that is propagating along the z-axis, the negative direction of the z-axis, so E2 plus jkz. That is in spherical coordinates E2jkr cosine of theta. Now, since this wave is regular everywhere, in particular, it is finite at the origin and also on the z-axis, and furthermore, it does not depend on phi. If we wish to represent this spherical wave function in terms of this wave function in terms of spherical elementary wave functions, we should employ for the radial dependence a Bessel function, a spherical Bessel function J, avoiding the use of y function or the Hankel functions, because those would be singular at the origin of the coordinate system. We should use, furthermore, a Legendre polynomial as to express the dependence on theta, because that's the only Legendre function of order of independent whose upper index is equal to 0 and therefore independent of phi, which is regular everywhere, so also on the z-axis. And furthermore, you can see there is no dependence on phi because of symmetry, and this is why the upper index of the Legendre function is equal to 0. So we know from these basic considerations that our plane wave should be written as an infinite summation of this kind of terms, in which the coefficients a sub n are still unknown, and our task would be that of finding those coefficients. In order to find the coefficients, we can employ the orthogonality of the Legendre polynomials. In particular, we multiply each side of the previous equation by p sub q of cosine theta times sine theta, and we integrate from 0 to pi with respect to the angle theta. We employ orthogonality to discover that all terms in this way will vanish except the term with index equal to q. And for this term, we would find that what remains at the right-hand side is proportional to Jn with argument kr, with the coefficient twice a sub n divided by 2n plus 1. Now, to find the coefficients a sub n, we could proceed in this way. We could differentiate the left-hand side with respect to the radial coordinate r, and then evaluate the result when r is equal to 0. If you do so, you would discover that inside the integral, a factor of cosine theta to the nth power pops out, and the result of this integral can be evaluated, as you can see here, in terms of these factorials and of these powers. Now, if you do the same on the right-hand side of the above equation, so you differentiate n times with respect to r, just a moment, I will admit Professor Frezza. Okay. You would discover, and you could do this as an exercise, that the result is the one reported at the bottom of this slide. So, and it depends, of course, on the unknown coefficients, a sub n. Now, if you equate the two results, you are able to find an expression, an explicit expression for the coefficients a sub n, which is very simple indeed. It's j to the nth power times 2n plus 1. So at the end, what we have found is the expansion of a plane wave, which is the left-hand side in the box, in terms of elementary spherical waves with coefficients j to the nth power times 2n plus 1, and the dependence on r expressed by spherical Bessel functions j with order n, and the dependence on theta expressed by Legendre polynomials with order n. Note that in doing so, we also have found a useful identity, that is the representation of a spherical Bessel function in terms of Legendre polynomials, as you can see from this integral reported below. So we have expressed the plane wave in terms of spherical waves. Another useful thing that we can do is to consider a source of spherical waves displaced from the origin. That is a dipole, as we saw before, placed along the z-axis at some distance r' from the origin, which we know produces a potential that can be expressed in terms of a zero-order wave function, h0, which is proportional to the free space Green's function. You could use either a z-directed vector potential, and in that case, the expression would be this one, or you could use the bipotential, so a radially directed vector potential, but also in this case, there would be proportionality to the zero-order wave function through a different coefficient, however. Now, our goal would be that of expressing this displaced wave function, that is a spherical wave that originates not from the origin, but from the dipole, so from some point along the z-axis, in terms of spherical waves centered at the origin of the reference system. Now, to do so, we observe that this wave function is rotationally symmetric with respect to the z-axis, so there is no dependence again on the phi coordinate, and it is regular at the origin, whereas it is outgoing when the radial coordinate is larger than r', which is the location of the source. And finally, this should be symmetric in the exchange between r and r' by reciprocity. So what we have is that our displaced wave function on the left-hand side of this equation should be written in terms of infinite summations, as you can see at the right-hand sides. Here we should distinguish when the radial coordinate is less than r', which is the above expression, from the situation when r is larger. You can see that the dependence, the radial dependence, should be expressed by a Bessel function j, because we wish the potential to be regular at the origin. Whereas outside the source, the dependence should be expressed by a Hankel function of the second kind, because we wish to have an outgoing behavior of the waves, that is, waves that propagate from the source towards infinity. By symmetry, the coefficients should be written in this way. That is, in the first case, we should introduce the Hankel function of argument k r', and in the second case, we should introduce the Bessel functions of argument k r', so that we have a single coefficient c sub n that can be used in both expressions. To find this coefficient, we may reduce this wave to a plane wave by letting the source go to infinity. If the source goes to infinity, that is, we consider the limit in which r' goes to infinity along the z-axis, so when theta prime is equal to 0, by exploiting the asymptotic representation of the spherical Hankel functions that is reported here below on the left, you would find that the spherical Hankel function at the left-hand side of the above equation tends asymptotically to this very simple result, which is a plane wave in blue, multiplied by this factor j e to minus j r' divided by k r'. Now, on the right-hand side, if you perform the same asymptotic limit, you would have the result that you can find here on top, in which the same coefficient pops out of the infinite summation. So we can equate the two sides and simplify the common coefficient. What remains is the blue part are the blue parts, which provides us with the desired expansion of a plane wave, which provides the result, because we can now employ the expansion of spherical waves that we derived before, and is reported here at the bottom. And then we can equate the two expansions, thereby finding by orthogonality the coefficients C sub n, which are very simple. They are just 2n plus 1. So all in all, we have the final result in which a displaced zeroth order spherical scalar function, H0, is expressed in terms of an infinite summation of spherical scalar wave functions of any arbitrary order, n. And this is the so-called addition theorem for the spherical Hankel functions. This is what we need to address in the second part of this lesson, the problem of radiation of a dipole in the presence of a conducting sphere. But now it's time to make our usual 10 minutes break. So see you in 10 minutes.
Ciao Paolo, il consiglio...
Ciao Fabrizio. Sì, immagino, ma io me ne sono andato prima.
Va bene.
Spero senza sorprese nella parte finale.
No. Non so se tu c'eri alla discussione con Marco Balucani.
No, quella l'ho persa.
È stato un po' descritto il fatto per cui Marco in qualche maniera decade dal ruolo.
Sì, ricordo, è vero.
Viene, diciamo, non so,
messo in un'aspettativa.
No, viene proprio...
No, proprio decade.
Come licenziato, diciamo.
Ma la cosa è temporanea o definitiva?
No. È definitiva, perché diciamo c'era questa incompatibilità e quindi nel momento in cui lui
prende questo ruolo,
alla gestione in qualche maniera di questo spin-off, secondo i nostri regolamenti deve decadere, quindi è avviata una procedura in sostanza per
la cessazione, sì.
Sì. Ecco.
Ho capito.
Quindi c'è stata un po' di discussione su quello e poi nient'altro, cioè su eventuali iniziative da parte del Dipartimento per protestare, perché comunque ci sono stati dei ritardi da parte dell'amministrazione, cioè se lui avesse saputo certe cose prima avrebbe potuto evitare la cosa. Invece gli hanno comunicato con ritardo e quindi non ha fatto poi più in tempo a quel punto a vendere le sue quote e quindi a poter rimanere professore come lui avrebbe voluto fare.
Questo è molto grave, però.
Sì, ma infatti diciamo che tutto riguarda i regolamenti, quindi non leggi dello Stato, regolamenti che ha fatto la Sapienza stessa. Un primo con cui si era scontrato all'inizio, quando avevano negato il carattere di, diciamo, spin-off universitario alla sua azienda, perché se invece gliel'avessero concesso lui avrebbe avuto tutta la facoltà di rimanerne, diciamo, amministratore. Quindi in una prima fase c'è stato un primo regolamento che ha bocciato questa cosa, un secondo regolamento che dava queste tempistiche per cui lui a questo punto
era fuori. Mi dispiace.
Era un po' la cosa più rilevante, poi non c'erano altre cose particolari, insomma.
Ok, grazie.
Prego, no, io poi non sono ancora riuscito a scaricare, se ho capito bene dove farlo.
Bravo, perché io ancora non ci ho messo le mani, quindi sono io in ritardo. Ma io pensavo di aver abilitato questa nuova cartellina che tu avrai trovato tramite il sito ILE corso.
Diciamo, io l'ho trovata la cartellina su Google Drive, in cui ci sono quindi le registrazioni recenti, appunto, di ottobre 2022, però non riesco a scaricare.
Le puoi solo vedere. Giusto? Ok. E io pensavo di avervi abilitato anche per lo scaricamento, però evidentemente ho fatto qualche errore, quindi ci devo rimettere le mani e appena lo faccio ti mando una mail e ti dico di riprovarci.
Grazie. E poi comunque anche fortunatamente la prossima lezione è di pomeriggio, cioè fortunatamente perché c'è l'assemblea di facoltà anche, però coincide con la lezione di microwaves e quindi non potrò seguire nemmeno a meno di non decidere di guardarla insieme agli studenti. Ecco, sto pensando
no.
sarà sempre sullo scattering, no?
Vabbè, sì, poi parlerò di cose pittoresche perché vi farò vedere l'arcobaleno e altre cose
allora,
simpatiche.
vedi?
Quindi se
No,
ti piace,
allora,
come no,
vai,
si può
vedi?
fare la mutuazione.
Hai visto? Ci collegheremo,
Ma che
diciamo,
bello.
riesco a proiettare sullo schermo, tanto ho visto che è alle 2:30, no?
Sì, alle 2:30.
Va bene.
Molto
Vediamo
bene.
allora. No, mi hai detto le cose pittoresche, allora diciamo
Sì.
dobbiamo farlo assolutamente. A fra poco,
Vabbè,
dopo.
a tra 5 minuti, sì, ciao ciao. Okay, I'm back again. Let us now consider the problem of a dipole radiating in the presence of a conducting sphere. According to this sketch, here we have a dipole with the moment I times L placed along the z-axis at a distance b from the origin, which is the center of a perfectly conducting sphere with radius A. In this problem, the symmetry of the configuration is such that the field radiated by this dipole will only have 3 non-zero components, and those are E sub r, E sub theta, and H sub phi, exactly as if the dipole were radiating in a vacuum. Now, the incident field, we have seen that can be represented in terms of a single Debye potential, which has therefore a radial component, A sub r, for the incident field, which is proportional to the free space Green's function, and it's also proportional to the radial coordinate r, and inversely proportional to the distance b between the source and the origin. And in particular, as you can see here in blue, the Debye potential is written in terms of the wave function psi a. And since we are working in spherical coordinates, and this is a spherical wave that is displaced from the origin, as we have seen at the end of the first part of this lesson, we can represent this spherical wave function of order 0 displaced from the origin by means of the addition theorem for spherical wave functions as an infinite summation of spherical waves centered at the origin of the reference system. Here, in this equation, I have introduced a notation which can be used to make things more compact, in which it greater than or it's the maximum or the minimum, respectively, between the quantities R and B. That is, when the observation point R is larger than B, then you should R is equal to R with the greater sign is equal to R, whereas otherwise it's equal to B, and the opposite when there is the less than sign in the subscript. Okay, this is the incident Debye potential. We wish to find the scattered field. So to find the scattered field, we should first determine the incident electric field on the surface of the sphere in order to enforce the boundary conditions there. Now, the electric incident field can be obtained by a differentiation process, because as you can see here in blue, this theta component of the electric field is proportional to the second derivative of the radial potential with respect to theta and r. So we employ the representation of the radial potential in terms of an infinite summation of spherical waves, and we differentiate these. In particular, with respect to the radial coordinate, we make a differentiation with respect to the adimensional quantity k times r, and the only thing we should differentiate is therefore the function j hat with argument kr, whereas the angular derivative is performed onto the Legendre polynomial p sub n. And we wish to evaluate the field at the surface of the sphere, that is when r is equal to a. Note that in the final result, there is here below in blue, the infinite summation goes from n equal to 1 to infinity, because the terms n equals 0 drops out, and that's because the 0th order Legendre polynomial p sub 0 is a constant, and therefore when you differentiate with respect to theta, that constant goes to 0. And note finally that in the notation I have used an apex to indicate the differentiation and derivative with respect to the argument of the function, in this case of the modified spherical Bessel function j hat. So this is the incident electric field. The scattered electric field can be obtained in the same way by employing a radial potential having exactly the same form. However, now we will use an outgoing traveling wave dependence on the radial coordinate. So instead of a Bessel function J, we will have a Hankel function, a spherical Hankel function H, here highlighted in red, of the second kind, from which, with the same algebra, we derive the scattered field on the surface of the sphere. And now we will have a spherical modified Hankel function H hat instead of a Bessel modified function J. We enforce the boundary condition on the surface of the perfectly conducting sphere by requiring that the total electric field along theta, sum of the incident and scattered parts, is equal to 0. This should be true for any value of theta from 0 to pi. And if you sum the two expressions of the incident and scattered fields by collecting them into a single infinite summation, and then you make use of the orthogonality properties of the Legendre functions, you would deduce that all the coefficients of these infinite terms in the summation should be equal to 0. So therefore, the quantity in square brackets in particular should be equal to 0. And this means that the coefficient, the unknown coefficient, C sub n, that describes the scattered field, is given by the simple expression that you can see here in the box below. So a ratio between two derivatives of the Bessel function J and the Hankel function H, with a minus sign in front of it. Once you have this expression, you can feed it back into the expression for the total potential, which is the sum of the incident and scattered potential. If you do so, the final coefficient, that is the red part, can be written as a single ratio in which the numerator has the form of a Wronskian, and by elementary properties of the modified Bessel functions, we find that this Wronskian is equal to the constant minus J. So the final expression for the total potential at the surface of the sphere, that is when R is equal to A, is given by the expression below in the box, where now you can see there is the Legendre polynomial P sub n that is multiplied by this coefficient, that is a ratio between a Hankel function, a modified Hankel function in the numerator with argument kb, and the first derivative of the same modified Hankel function with the argument ka in the denominator. This is the total potential, from which you can find the total field by using the standard relations that give you the fields in terms of the bipotentials. And those relations are reported here for this particular case. They are particularly simple, and they involve differentiations with respect to the angular variable theta. Those differentiations can be carried out as infinite summation, because the series involved is uniformly convergent with respect to the angle theta, and therefore it's feasible to differentiate. So if you do so, you will obtain a series representation for the electric field and for the magnetic field. So this is the formal solution, the final formal solution. And now we are in the position of introducing the so-called Watson transformation, and through this transformation, the definition of a creeping wave. The solution we have obtained is a complete and exact solution to the problem of a dipole radiating in the presence of a perfectly conducting sphere. However, even though mathematically exact, this has some important drawbacks. In fact, the solution is expressed as an infinite summation of terms which are called partial waves in the literature. And this summation may have a convergence which is very slow if the sphere is large, in particular if its dimensions are large in terms of the free space wavelength. One could check that the number of terms that is needed to start having a reasonable convergence is of the order of the electrical length of the radius of the sphere, that is, of the quantity k times a, that is 2 pi times the ratio between the radius of the sphere and the free space wavelength. And depending on the problem, this number can be very high, for example, thousands or even more than that. Now, this is, of course, not a problem, since we have digital computers for evaluating infinite summations up to any number of terms, but it was a problem a century ago when the first scientists started to consider this problem. In any case, a solution expressed in terms of thousands of partial waves would give us no physical insight into what's happening in the wave processes of this configuration. And so this is a nice quote from the great scientist Eugene Wigner. In order to get this physical insight, we could do something, as I will try to describe in a moment. Just to give you the motivation for the work of Watson in order to modify the form of the solution, I will mention you that at the beginning of the 20th century, Guglielmo Marconi performed a number of very famous experiments in which he showed that it was possible to communicate through radio waves beyond the horizon. In particular, in his experiment of 1901, he was able to communicate between 2 points which were not in line of sight distance, considering that the sphere that may represent our planet, the Earth, has a diameter of the order of 12,000 kilometers, or more than that, actually. And that Marconi employed wavelengths around 350 meters because he used oscillators working at around 850 kilohertz. Then the normalized radius of the Earth at this frequency, k times a, is of the order of 10 to the 5th power, which is the number of partial waves that would be necessary to sum in order to find a reasonable convergence for the solution we have derived. So what was first proposed by Poincaré and Nicholson in 1910 and then developed in a systematic and rigorous way by George Neville Watson in 1918, and after him by Sommerfeld as well, was a method which consists in replacing the original solution in terms of a partial wave series by an integral. And through this integral, evaluate the integral in particular, the evaluation of the integral can be obtained in an approximate way by using the calculus of residues, and thereby obtaining a rapidly converging series alternative to the original slowly converging one. This is the original paper by Watson that I will follow in the next few slides in order to show you how to proceed. The key idea is to consider the partial wave series for the radial potential, that is the exact solution for the total potential that is reported again on top of this slide. In particular, in red, I have written its general term that depends on the index n, and to consider this term as if it were obtained as the residue of a suitable function in some of its poles, in one of its poles. That is, we write the red term of the infinite partial wave series as the residue of some suitable function f of some complex variable s, which is an auxiliary variable. Well, now s must have, this function f must have poles at the locations n plus 1/2, so at the half integer abscissas along the real axis. What Watson used was this specific function f. That's not the a unique choice. That's not the only possible choice for the function f. But he used this particular expression in which, as you can see, whenever you had the index n in the original expression, you have a function of s in this modified in this function f. In particular, this complex variable s occurs in the indices of the Legendre polynomial, as well as of the modified Hankel functions in the numerator and in the denominator. Now, why treating these partial waves as residues of a holomorphic function, of a complex function? Well, because now we can study this function, in particular its singularities, and its singularities are poles, and poles of two kinds. The first family of poles comes from the cosine in the denominator, and those are exactly the poles that correspond to the partial waves in the partial wave series. But in addition to those poles, and those are an infinite number of poles, there is also another infinite number of poles. They come from the other term, the blue term here in the denominator, that is from the derivative of the Hankel function having order s minus 1/2. We will indicate this second family of poles with the symbol ni sub n. And there are no other poles because all the other functions occurring in the expression for f of s are entire functions of the complex variable s. Now consider the location of these poles in the complex plane. The poles associated with the cosine are evenly spaced on the real axis at half-integer locations, whereas the other poles form a family, the blue ones, that is displaced off the real axis. They are in the first quadrant of the complex plane, and it can be shown that when Ka is large, that is when the radius of the sphere is large in terms of wavelength, this second family of poles lie close to the broken line, here represented with a gray line, whose equation is reported at the bottom of this slide, and that line originates at the point with abscissa Ka along the positive real axis. Now, what's the procedure that Watson followed? He considered a family of contours in the complex plane of the s variables, of the x variable, like the red one reported in this slide, that goes along the vertical imaginary axis from the minus jm to plus jm, where m is an integer that goes from 1 to infinity. So we have a family of contours, and that is closed by a half circle that goes on the right. So it goes in the first and fourth quadrants of the complex plane, such that this half circle does not intersect any of the poles. Now, the integral along the imaginary axis, the portion, the vertical portion of this integral is exactly 0 because the integral is odd as a function of s. So this gives no contribution. Furthermore, one could show that by increasing the index m to infinity, the half circle would become an infinite half circle, and the integral along this contour can be shown to be infinitesimal. So we can neglect the contribution of this integral when we let the radius of the circle go to infinity. So all in all, the entire integral is equal to 0. However, the integral now, the integration contour now encloses all the poles, those on the real axis as well as those off the real axis. So by using the residue theorem, the value of the integral, which is equal to 0, must be equal to the sum of the residues at all the poles contained on the right half plane, where the real part of S is positive. But those poles belong to the two families, the red one, that are the poles on the real axis, and the blue ones, the poles in the first quadrant outside the real axis. The sum of their contributions must be equal to 0. So therefore, in other terms, the sum of the red poles on the left-hand side of the bottom equation should be equal and opposite to the sum of the residue contributions at the other poles, the blue ones. And this is the trick that Watson used to replace the original series, which was given in terms of the residue at the red poles, with a modified or transformed series, which is equal to the sum of the residues at the blue poles. And those residues can be found easily because whenever you have a function that is the ratio of a numerator 0, say, then you will have a simple pole of the function, of the rational function at the same location, and the residue at the simple pole can be computed easily as the ratio between the numerator evaluated at the pole location and the first derivative of the denominator at the same pole location. You can show this as an exercise. So all in all, the residue contribution, as you can see here in the blue expression, is written in terms of functions, in particular of the derivative of the Hankel function h prime with respect to s, where now s occurs in its order here, so it's a complex order. What we have obtained finally is reported here in the box, is an alternative representation for the total potential. Instead of a partial wave series, what we have is another infinite summation, the blue one, which could seem more complicated than the original one, because one should find numerically the location of the blue poles, n sub n, in the complex plane, and also one should evaluate numerically the relevant residues. However, when the electrical dimension of the sphere is very large, this series converges extremely rapidly. Sometimes a single term of this series is enough to have a very accurate representation of the total potential. So we need only a few terms of this series. And so we obtain something that is numerically very convenient. And as we will see in a moment, is also capable of giving us some physical insight into what's happening. In particular, if you consider the angular dependence of each of these blue addends here that is contained inside the Legendre polynomial with order n sub n minus 1/2 with argument minus cosine theta. And if you consider what happens in the asymptotic limit when the absolute value of the pole n sub n is very large, which is true whenever the sphere is large electrically, and if you observe things sufficiently far from the north and south poles of our sphere, so you are not exactly at theta equals 0 nor at theta equal pi, then by some not trivial asymptotic considerations, you would find that the Legendre polynomial at the left-hand side can be approximated asymptotically, as you can see on the right-hand side, where I have highlighted in red the terms containing the phase variation. And as you can see, the phase depends linearly on theta, and it's expressed by this complex exponential, which expresses a traveling wave behavior with respect to the angular variable theta. So what we have is an azimutally propagating wave. So that is a wave that propagates along the sphere along the direction theta. And it does so with a wave number along theta given by the value of the pole location n sub n, which is in general, as we have seen, a complex location. So we have a complex azimuthal wave number. This is what, for the first time, France in the 50s of the last century indicated as a creeping wave, because actually it's a wave that propagates remaining close to the surface of a curved surface, and therefore it creeps along it. And due to its complex wave number, this wave attenuates during its propagation. This is due to radiation that occurs tangentially with respect to the sphere at any point during the propagation of the sphere. So from this point of view, a creeping wave is similar to a leaky wave, because also in this case we have a complex wave number that accounts for radiation. In this case, however, radiation is due to curvature, that is the curvature of the surface, in this case of the sphere, rather than to other radiation mechanisms as those we have described in connection with leaky waves. Some final remarks before concluding the lesson. The first one is that in quantum mechanics, the integer index that occurs in the Legendre polynomials, that is in the angular terms of the partial wave expansion, is associated with the so-called orbital angular momentum of the wave function or of the particle you are describing. So if you assume n to that if you allow n to assume complex values, that is what is done in this Watson transformation, you can say that you are working in the complex angular momentum domain. And actually, it was an Italian physicist, Tullio Regge, who was the first at the end of the 50s to introduce the study of the analytic properties of quantum scattering as a function of this complex angular momentum. And this was the birth of a whole theory, the so-called Regge theory, that was developed in subsequent decades and was particularly in vogue in the 60s. For this reason, the poles that are used in the Watson transformation may also be called, and are called in the literature, Regge poles. The second remark concerns the original problem, the problem of radio wave propagation beyond the horizon, because after Watson proposed his method, he discovered that the rate of azimuthal attenuation of the dominant creeping wave was actually very large if compared with the attenuation that was observed experimentally. That is, basically radio waves reached the receiver beyond the horizon much less attenuated than the Watson transformation would predict. And actually, they started investigating the reason of this discrepancy, and it turned out that the problem was in the physical model. The physical model consisted only of a source and a conducting sphere, but the problem is that what is actually crucial in the propagation beyond the horizon is the existence of a second spherical shell concentric with respect to the Earth, that is constituted by the ionosphere, that is the layer of our atmosphere which contains ionized gas, and this layer at certain frequencies is able to reflect the electromagnetic waves. So basically, the boundary conditions of the problem are different, and what happens is that the source, the transmitter, basically excites waves that are bouncing back and forth between the ionosphere and the Earth, and therefore the space, the spherical shell between the two layers, the Earth and the ionosphere, behaves as a waveguide. That is a sort of spherical waveguide, which is also known in the literature as the Earth ionosphere waveguide. And for this reason, the attenuation is much less than the one associated with creeping waves, because it's the attenuation typical of a waveguide that exists only because of losses inside of the media. Okay, this concludes our discussion of the spherical waves and the Watson transformation. Next time, I will generalize this latter example to the case of scattering from dielectric spheres, that is, from penetrable spheres, first discussing the case of a perfectly conducting sphere and then generalizing it to the case of a penetrable one. And the application of this scattering problem will be the discussion of the rainbow, which is a beautiful phenomenon that all of us are familiar with, and of a similar phenomenon, which is more subtle and more difficult to describe mathematically, which is the so-called optical glory. So see you in the next lesson during the afternoon of Thursday. We will see exceptionally at 2:30 after PM because of a concomitant faculty meeting, and we will do our last lesson in this course. Thank you very much.
Grazie, arrivederci, professore.
Arrivederci.
Ciao Paolo, grazie.
Ciao, buona giornata.
Anche a te.
Arrivederci a tutti. Riccardo, avevo dimenticato di metterla nella prima mail, spero sia stato raggiunto dalla seconda, se mi sente.
Mi è arrivata l'email, soltanto che non mi sono riuscito a connettere in tempo perché non riuscivo a collegarmi e-learning, non so perché non mi poteva collegare.
Ah, strano, mi dispiace. Comunque è stata registrata la lezione, quindi la può trovare. Buona giornata a tutti. Arrivederci.
Thank you.
Grazie, professore.
Thank you.